But now we have Pablo going to advertise a different workshop. And Pablo is an expert, of course, in inverse problems, control, and currently a professor at MIT.
Anyway, so I guess maybe some of you were in the first edition of this workshop, kind of earlier this year. So the second version is going to happen at Berkeley, next June. And I guess the most important thing that I should point out is that we'll be having papers this time. Deadline is November 15, so start writing your best papers and send them there. The official call for papers will be out shortly. Right now, if you go to this website, it will redirect to the MIT version last year, but we'll switch it very quickly.
Wait, Sean's worried about the deadline. Wait, how about, I figure we could start, if you start November 7th.
He can write a paper in 2 minutes. Yeah, you should not worry about this. Anyway, so my background was actually control theory. I guess I've been doing more optimization this time, so I feel guilty that I will not be talking about control. But I'll be talking about some very nice work, actually, with my very talented student, Jason, that has to do with actually some pretty basic questions in machine learning and Gaussian kernels. And it's kind of interesting how much mileage one can get out of this, even though there's been a lot of work, I think, in related areas. So what's the setup? Let me just describe a mathematical question which happens not just in machine learning, but also in scientific computing, which is trying to understand how to compute what's called a Gauss transform. So what is a Gauss transform? Is a very nice operation. It's really like essentially a computation of the following type, where we have some points. I guess I'll describe it in details in a second. But the setup is I'm working on some d-dimensional space. So think of d as some fixed dimension. And I have a certain points x sub i's. I have a certain points y sub i's. And somehow associated to my points y sub I in there, to each point, I have a certain strength, q sub j, and a certain width of my kernel. And what I'm really trying to compute is somehow this function of x. Right? For every point x, I really want to compute exactly this weighted sum of the Gaussian potentials centered at the points y sub j at the point x. Right? So in principle, it's just a simple expression. Perhaps we're writing in here more formally, given these target points x1 to xn, and my sources, which represent somehow the points where my Gaussians are centered, y1 to yn. What I'm trying to compute is exactly this Gauss transform at each one of my points, x sub I. Right, so in principle, of course, this doesn't seem terribly complicated. You just exactly evaluate this sum. What is the problem in here that typically n, maybe in the order of millions, right? And you want to try to compute this in some kind of efficient way. This is really the bottleneck task in many, many applications. If you try to do ridge regression, support vector machines with this kind of kernels, kernel density estimation, Gaussian process regression, PDEs, optimal transport in particular, and I tell you why somehow we actually, or Jason really got interested in this problem.
When you say efficient, what do you mean? You have an n size input. Do you want
Yes.
it to be faster than n?
I'll talk about this in just a second. In the setup that I talk about in here, I actually want to compute things to a pretty small error, so I will not be able to use sublinear type things.
So why is this called a transform, which looks like a function?
Sorry?
Why is it called transform?
It's a linear map, if you want, because to every points x sub I, you associate a number. Okay. I mean, it's like Fourier transform, right? It's just a linear map. Okay, good. So what is the issue? If you try to do some direct computation, this is will take order of n squared, which if you think of n being order of millions, this is actually not possible. So what is the natural question? Can we do this in a faster way, perhaps in some kind of approximate manner? Right? So here's perhaps I think a simple mathematical formulation. What are we really trying to do? Somehow we're trying to compute exactly the product of this matrix K with my weights Q1 to Qn. And the entries of this matrix depend very explicitly on the points x sub I, where I want to evaluate my transform, and the points y sub j, where my Gaussians are fixed. Right? So somehow what I really want to do is to both form that matrix and compute that product efficiently. Now, what is the challenge? That matrix is size n by n. So if I even think about forming that matrix, of course, I'll have to do at least n square operations, but I really don't want to do anything that's kind of order of n square. Right? So what is a natural approach that one would think if you try to do anything like this? Good. Then perhaps what one could try to do is to form some kind of low-rank factorization of that matrix. Because if we were able to compute some kind of low-rank factorization of that matrix, let's say for some of size n times r from some fixed r, then we would be able to do all these kind of operations in linear time in n. Right? So part of what we'll do, and there's been a number of approaches somehow in this direction. I'll tell you a little bit about the work and how what they're doing actually differs from this. But the very natural question is how to form this low-rank factorization without actually ever computing this matrix. Right? You don't want to do an SVD. You cannot really, in a sense, touch these matrices. So there are some of the algorithms, or the, if you want, families of algorithms that do these kind of things. Tailor features, a method essentially based on some kind of Taylor expansion of the Gaussian kernel will do something like this, and I'll say a little bit more about this. Nystrom methods where you subsample some of the points and compute some kind of approximate factorization of that matrix is also a possibility. Random features, they try to do also some kind of approximate factorization of this. There's a very nice and very interesting family of methods based essentially on fast multipole methods. So those are, I will not explain in detail what those are, but they're a little bit more subtle than doing a global low-rank factorization of this matrix. So essentially what they do is they do some kind of partitioning of the space, and they combine these local low-rank factorizations into some kind of big object with some kind of tree decomposition of the space. And those are very efficient in some setups. But what I really want to talk about is this new algorithm, or this kind of family of methods, if you want, that they're doing, that actually perform significantly better than many of the things in the particular setup that we're interesting, which is where you're doing relatively low dimension and high accuracy. Right? So think again of dimensions, perhaps up to 8, 10, 15, something like this, and you really want high accuracy. You don't want to do something like, for instance, random projections that will do actually where it's impossible really to achieve high accuracy in these kind of problems.
Dimension of x, you mean?
Sorry?
When you say the low dimension, you mean the dimension of x and y?
D, the dimension D. So for instance, in that range, also anything like fast multipole will not work, because you cannot really do partitioning of the space in that dimension.
So
D, not
D is more than 3, but less than 100. Is that what you mean?
Yes. No, even D equals to 2, even 1.
D?
No, multiple works up to dimension 3, 4.
Right, exactly.
Yeah.
So you were talking about
Yeah, exactly.
But not millions.
No, and actually nothing works in that region.
Fair enough.
So why do we care? Again, one of the motivations is exactly just Gauss transforms in general. Why do people care about, for instance, in ML? It's exactly in the context of trying to do perhaps training a kernel machine. So what are the basic primitives that you need to do in that case? You essentially need to solve linear systems that are associated with this kernel, or really like some perturbation of it. Of course, you don't want to do this in dense algebra. That will pay either a quadratic or cubic price in time or memory in terms of n. But if you have, of course, some kind of factorization of that matrix, then essentially by doing matrix inversion lemma type things, you can solve these kind of operations paying only a price that will depend on the rank of your factorization, not actually n. And the same thing is true for the testing case. I mean, not just when you want to do training, but even in the testing case, having some kind of factorization of this will actually allow you to do things more efficiently.
You always want to compute the exact answer, right?
No. So I want to compute, if you really want the exact answer, then you really cannot do anything. If by exact, you truly mean exact and not machine precision. right? Like, kind of.
Okay, for me, machine precision.
Okay, then it's perfectly fine. I mean, if you're, well, but then there's no difference between machine precision and approximate, right? I mean, for you, like, kind of, I mean, no, approximate means 10 to the minus 15, right? Machine, for you, exact means.
I'm thinking like, would you have like an epsilon?
Yeah, epsilon squared or log 1 epsilon.
Yeah. Okay. Yeah. So in here, if you want to do 10 to the minus 15, that's fine. These algorithms are going to work. These are not 1 over epsilon squared type algorithms. These are log 1 over epsilon.
Excuse me.
Yep.
The low-rank factorization that gives good approximation for multiplication is not necessarily gives good approximation in inverse.
Absolutely.
Right?
Like,
Do you give like 2 variations that works well in inverse as opposed to like multiplication?
In here, like, essentially, I'll talk about, like, our notion of approximation, like, kind of, but it will imply, for instance, actually, if you apply, in that case, it will really depend on the regularization, right? How much you regularize. Because, again, if k is low rank, somehow, like, kind of, there's no.
If you don't, but if lambda is 0.
Then it's only part, right? And neither is original kernel. Right? The original kernel is going to be very, very close to it. Okay, good. So let me tell you about, like, kind of actually the application that motivated Jason to actually look into this. He did some very nice work before in terms of optimal transport and matrix scaling. So what's matrix scaling is a problem that I guess perhaps some of you are familiar with. Like, you have some non-negative matrix, and you have some target distributions R and C. So what you're trying to do is to scale your matrix with diagonal scalings on the right and the left in such a way that the sum of the rows of your matrix and the sum of the columns of your matrix are equal to the target distribution R and C. So it's kind of a very well-known problem. If you want, like, kind of just for concreteness, think about the case when R and C are the uniform distribution. Essentially, what you're trying to do is, given a non-negative matrix, to rescale your matrix with diagonal scalings in such a way that it's doubly stochastic. Right? It's a very well-known problem. There's a famous algorithm for doing this, Sinkhorn algorithm. So what is Sinkhorn algorithm? Essentially, you iteratively rescale rows and columns. And what is the basic operation that you have to do in that case? Essentially, you have to compute the sum of the rows and the sum of the row sum and the column sums of your matrix. What is that? That is really multiplying your matrix by the all ones vector. So it's exactly, like, kind of an operation of this type. So if you have a good fast primitive for, like, kind of computing this Gauss transform, then that essentially gives you fast algorithms for optimal transport, for computing L2 Basel sign matrix. Right? Good. So let me abstract, like, kind of now these 3 applications. Let me just talk about the mathematical problem that they're trying to understand, which is given, like, somehow my kernel, my matrices, my Gaussian kernel in there. What I really want to compute is some kind of factorization of it that will be useful for the kind of things that we want to do. Now, of course, there's a lot of ways of factoring a matrix. In particular, one of the things that we do know is that there's an eigenvalue. We exactly know what the eigenvalues of the Gaussian kernel are. We exactly understand, like, how to factorize it. Now, what is the difference and, like, what's the opportunity, if you want? That for many of these applications, what we really want is to control the entrywise error. What we really want is to produce some kind of low-rank factorization that has a small entrywise error with respect to, like, kind of the original kernel. Or if you want, think about, like, kind of, if you just think in terms of matrices, you want to produce a low-rank matrix in there in such a way that the L infinity error between your matrix and K is as small as possible. Right? So in particular, why? Think about in the optimal transport case, it turns out that you can control. If you can control this error, you can control how what is precision, if you want to, with your computing this approximate solution of it.
So if the goal is to multiply these matrices by a vector, then the element-wise errors could cancel out when you multiply it by a vector. So isn't there a better norm that takes into account matrix vector multiplication errors instead of element-wise?
It depends on what you know of that other vector, right? So for instance, for transport, what you know is that other vector is actually an element in the simplex. right?
But if you know it's all ones, or there's some Q's that you actually wrote down yourself, so you know them.
So it depends, again, on what are you willing to assume of that. If somehow that vector can be absolutely arbitrary, and the only thing that you know is some constraint on the L2 norm, then yes, of course, the induced L2 norm is good. If you know something about the entry-wise errors, about the size of the entries of that vector instead, then some kind of other norm will be appropriate. But let me also make a point, and this is actually perhaps more of an empirical point, that even though somehow the approximations that we want to use are motivated by entry-wise error, they actually perform really well, even if you care about spectral error, even if you care about any kind of other error measure. And this will actually become clearer, I guess, in a second. Good. So the other point that we're very, very explicitly going to exploit is that typically, in the finite case, of course, you can always assume that your domain is bounded, right? That all my points are some domain, and of course, you can scale it in such a way that all your points are, let's say, the difference between any 2 points is less than or equal than 1. And this is quite important because things like an eigenvalue decomposition will not actually exploit this, right? Yep.
So is it also obvious for the kinds of motivating examples you have that high precision is the regime of interest?
It depends on what you want, and it depends on what, that's one of the things that that's interesting about this problem. There's many different regimes depending on what you want to do, and different algorithms, they're better in different, regimes. If you want high dimension, hashing type methods approximate nearest neighbors. If you want, low precision, high precision, low dimension, this kind of. It's a bit complicated, I think that, or not. There's many facets. Let me say it this way. Okay, good. So what is perhaps the approach that we're going to use? Is really, as I said, we're not going to care so much about the points themselves. We're really going after a factorization of the whole kernel. In a sense, the location of the points is not going to be terribly important for us. What's really going to matter is that there's in some kind of ball. Let me just contrast this, because it's important, to methods that are perhaps data adaptive, right? Where you can see your points first, and based on your points, you pre-compute something. And we're not going to do anything like this, and there's reasons why in certain situations that will not help. So as I said, what we're going to want to do, given the Gaussian kernel, we're going to produce some kind of other approximate kernel in such a way that this entry-wise error is as small as possible. So how are we going to do this? There's really 3 key ideas, and I think each one of them, actually they buy you a lot compared to some of the things that people have done before. So the first one is we're going to use some kind of efficient low-degree uniform polynomial approximations. So this really comes from approximation theory for trying to understand, when you have a function, how you approximate functions well in L infinity, right? Not just in doing some kind of expansion like a Taylor expansion. The other point, which is actually you get a lot of practical mileage out of this, is you have a better control of what happens when you have a low-rank matrix and you apply a polynomial entry-wise to it. And we'll see exactly what I mean in just a few slides. And the third one really has to do with not just doing things at the level of exact arithmetic, but actually worry about numerical conditioning issues. And that's where things like spherical harmonics are going to come into place. So let me try to explain the details. I'll do a little bit more, I guess, regarding the first 2. So the first one, as I said, really has to do with trying to understand how to approximate functions well with polynomials, right? And again, my notion of approximation is really pointwise, right? I really want the L infinity error at every point. And as I said before, we're working in some compact situation. So t for me, for instance, is going to be in -1, 1. And I'm really trying to approximate a univariate function, with a polynomial. Remember, my Gaussian kernel is e to the t squared, so I really only need to worry about the exponential part, right? The exponential. So what's a naive way of trying to approximate, the exponential function is to do a Taylor expansion, right? That's very easy. As somebody would say, it's so easy that even a computer scientist can think about doing this. But this is not good. So why doing a Taylor expansion is not good? Can anybody tell me why, if I'm interested in doing some kind of entry-wise approximation of the error? I want a uniform approximation of the error.
Simply not uniform.
what's also happened exactly, that Taylor approximation is really, really good around 0, if I expand around 0, but the error, kind of when t gets closer to 1, is going to be very large. Sorry?
You're going to have ripples.
No, I will not have ripples if I want to do the approximation of the exponential. I want to have ripples, because ripples will give me a smaller error. But kind of the Taylor expansion actually will not. But will happen, I'll show you plots in just a second, is that what you'll do, you'll get really good error around 0, because that's exactly what the Taylor expansion wants to do. It wants to be very, very precise in a neighborhood of 0, but the price that you pay is that the error outside is going to be large. Of course, if you keep the degree up, the error eventually is going to go down, but kind of, it will not be good. What is the right way of doing this? Kind of people in numerical analysis know this for a long time. What you want to do is a Chebyshev. I mean, you don't want to do this. What you really want is exactly that. Kind of like the best L infinity approximation. You cannot do. I mean, it's a convex problem, but it's not very easy analytically. So one thing that you can do that actually performs really, really well is to do what's called a truncated Chebyshev expansion. Right. So what you take your function, you expand it in Chebyshev polynomials. It's very much a series like the Taylor series. And what you do is you're going to truncate this series at some point, and that is going to give you a polynomial of the Rn that's going to approximate the function that you want really, really well. Right? Why? Exactly what you were saying. Because somehow the oscillations of Chebyshev polynomials are going to tell you that this approximation is really good. I'll show you plots in just a second. We all know what the coefficients of the Taylor expansion are for the exponential. The question is, what are the coefficients that we're going to put in here? So how do we compute this? It's kind of, luckily for us, people have done this 150 years ago. Why? Because computing Chebyshev expansions is really doing Fourier series in disguise. Right? If you do a cosine change of variables or whatever, then computing Taylor expansion, a Chebyshev expansion is exactly like computing a Fourier series. We have to compute the Fourier series of that function that has a name. It's called a Jacobi-Unger expansion of the exponential. And it looks something like this, where these coefficients in there are some special functions, or called the modified Bessel functions of the first kind. It doesn't really matter. Any software will compute those things for you, and there are some numbers. Let me not tell you what they are. So what's the approximation that you want to do? Essentially, you take that series and you truncate it. What that will give you is a polynomial of degree n that's going to be a really good approximation to the exponential. And what do I mean by really good? So for instance, in here, what we're doing, I'm plotting the difference between the exponential and the Taylor expansion. And this is, for instance, what that looks like. The blue line in there is the error of the Taylor expansion. Notice that this is log scale. And this is exactly what I told you before. The error is very, very small, below machine precision, around 0. But it gets pretty large in here. On the other hand, kind of the error of this approximation, of the Chebyshev approximation, is nearly, it's much smaller, and it has this equi-ripple property. Right? And just to give an example, even if you take, for instance, polynomials of degree 8, which is not very much, you get an error which is 260 times smaller if you do this kind of approximation, which is again a polynomial of the same order as a Taylor expansion, but this is incredibly bad.
Since you're going to talk about sort of computational complexity,
yeah.
Computing LK of alpha, do you want it to be like it's an order of alpha operation?
Oh yeah, no, this is all easy.
All this is like order 1.
Yeah. Essentially, yeah. If you do this in machine precision, this is not an issue. It's like computing sines and cosines. It's literally as complicated as computing sines and cosines. Okay, good. So what is the point in here? You get much better precisions. And let me mention also why people cared about this before, because actually it will come back later when we talk about somehow how to actually implement this. So what's the other name? If you talk to anybody in physics, they will know about these expansions, because this is exactly what's called a plane wave expansion. Right? What this expansion does, if you rewrite it in a different way, gives you exactly a way of writing a wave, a plane wave. Right? What this is exactly like, kind of A is a vector, so this is a linear function of x, and then you apply like, a cosine to it, so it's really a wave that depends on a single dimension. And what you write is as a linear combination of terms of a product of terms that depend only on the radial direction and terms that depend on the angular direction. So this term depends only on how far you are from the origin. This term depends on the direction in which you are. And essentially, you're decomposing any wave in that form. And somehow, for instance, what you have is exactly the partial sums of that, like, kind of at different levels of k. As you can see, as k becomes larger, as the limit of that sum becomes larger, what you get is more and more like, kind of exactly this linear approximation. And we'll see this coming back. Like, kind of these are essentially going to be the features that we're going to use whenever you actually implement this. Yeah, sorry, you had a question.
Figured it out.
Okay.
Yeah. This is starting to look like the random Fourier features that you.
Yes and no. We'll talk a little bit about. Yeah. So there is a difference. I mean, there is of course an important difference with Fourier features in here. Like, the random part of Fourier features will actually appear in here. It will not appear somehow in the. Yeah. Let me talk about that later if you want. Okay. Good. Just more pictures, just to make it clear that the things converge really quickly. What do we have in there? Blue line is the exponential. These are the polynomial approximations of degree 1, 2, 3, whatever. And as you can see, the error very, very quickly gets to 0. Same kind of things, just also to give you an idea, as a function of the error that you want, the epsilon that you want, and the width of the kernel. This will tell you what degree of a polynomial you need to approximate it to that given precision. And as you can imagine, or you would expect, you have this nice dependence that as the width becomes larger, the easier it should be to approximate it with polynomials of some degree. If the kernel becomes very narrow, then it should be more difficult. And there's explicit quantification of these trade-offs if you want, but these numbers, I find these numbers to be somehow they tell nicely the story. Okay, so what's the summary of the first part? If you ever want to do anything with Taylor, throw it away. Taylor is a horrible thing to do if you want to approximate things uniformly. It's really bad. You don't want to do this. Any approximation theorist will tell you that that's stupid. And there's other expansions. In this case, I have fancy names, but they're really about trying to approximate things uniformly in a nice way. Now, what is important for us? On the one hand, the error decays super exponentially, in terms of the truncation degree. It's a lot better than, I think, many things. And this is super crucial. The decay of the coefficients in here, they're independent of the dimension. So if you were to look at anything like kernel eigenvalues of the Gaussian kernel, the dimension in there appears very, very explicitly. If there's nice formulas about, the dimensions of the eigenvalues of the kernel, and dimension hurts you. In this case, because really you're trying to approximate the 2-point property, right? Just giving x and y, the only thing that you care about is a line between x and y. Then you don't pay a price for the dimension in there. You'll pay eventually, of course, you have to pay a price for the dimension, and we'll see in the next part where it appears, but in here it doesn't. And it's super explicit, right? What's the second part? There's this really folklore. I mean, there's this fact, that if you have a matrix which is low rank, and you apply a polynomial entrywise to it, then the resulting matrix is also low rank. I mean, the rank increases, but in a controlled way. Right, and one can make it very formal. If you have a matrix of rank R, you have a polynomial of degree n, and you look at the entrywise application of this polynomial in the matrix. And the new matrix has rank at most that number, R plus n choose R. And furthermore, this bound is tight in the sense that you can produce matrices for which is achieved. Now, why do we care about this? Because, of course, what we're interested in what happens when you apply this polynomial, this approximation to the exponential, to the matrix x minus y squared, right? So the matrix with entries x minus y squared has rank at most d plus 2, because it has this explicit factorization. So what that means is if you use a polynomial of degree n to approximate the exponential, the resulting matrix will have that rank. Right? Or it will have at most that rank. Right? So this immediately tells us, I guess a basic form of the algorithm, right? You use
N is typically small, or N is typically larger.
Sorry?
N is much. N is large here? Or
It depends on the regime. Again, in the high dimensional case, typically n is small. It's actually embarrassing. Many of these papers about kind of approximate, Jason was telling me, many of these papers about trying to use the Gaussian kernel in the high dimensional setting or whatever, they actually use linear approximations of the kernel. So their approximation of the Gaussian kernel is a line. Yeah.
I was worried that could be quite large, right?
Again, the setup in here is that the number of points is huge. And that number may be 10,000 or 50,000 or whatever. And you still gain a lot. Now, what is the problem? So, what is the statement? In there, the slide says that the rank of that matrix, and you use a polynomial approximation of the Vn. If you get a matrix of that rank, actually, if you code it up, you empirically observe a much lower rank. And if you work it out, the number ends up looking like that. So you may think, okay, both are huge binomial coefficients. But if you actually compute them, let's say, for instance, for dimension 2, polynomials of degree 20, the difference between the first bound is something like 10,000. And the second number is something like 400. Right? 25 times smaller, an algorithm that's 25 times faster. So what is the difference? Somehow I told you that there was this lemma and that this was actually tight. So what is the difference really that in here, you're applying that polynomial not to an arbitrary matrix, but you're actually applying it to a particular matrix. Right? So think about the case I told you before that if you apply a polynomial to any matrix, to a generic matrix, that will be the correct bound. But in here, this matrix x minus y squared, these vectors a and b, they have this form. And these vectors a and b are not generic. Right? They live in a certain variety. They satisfy certain relations. If you take the sum of the squares of the first entries, you'll get essentially the dth plus 1 entry squared. Right? So they live in a particular variety in there, and you're applying a polynomial to this, and what this causes is drop in the rank in there. Let me see. I finish what time? Just to make sure. 3 something? 3:05? 3:20? No.
3. Sorry.
Okay, yeah, 3:05. Yeah. Okay, good. So 3:20, I should have taken it. Yeah. Yeah. Okay, so let me, just so we can understand a little bit this difference, let me give an example. Right? Again, super concrete. D is equal to 2, n equal to 2. So I apply this quadratic polynomial entrywise to a matrix. If you apply this to a generic matrix, absolutely generic matrix, P of that inner product, the entries are going to look like this. When you expand that out, this is going to look like this. And if there's no relations between the variables a sub I and b sub I, somehow what happens is that when you expand these terms, somehow there's no identities. There's no relations that you can actually exploit in order to reduce the number of terms that appear. So what will happen is that that sum in there, it has 15 terms, and that's exactly what this lemma is going to tell you that you can do. On the other hand, if you apply this polynomial, again a generic quadratic polynomial to a matrix of entries x minus y squared, again we're in the case of dimension 2, and you expand all that expression, you can very cleverly combine terms in such a way that what will happen in here, when you look at that expression, and again, think about fixing the y terms and look at the span of the vectors, at the span of the functions in the x space. What you'll have is that all the terms in there have the form some function of y times some function of x. And the only functions of x that will appear if you write things in that form, they're going to be things of this type. Right? And furthermore, so really what I'm interested in is what is a span of these functions in there. And furthermore, this norm of x squared is in the span of these other two terms. So what happens in here is that the rank of that matrix is going to be the span of these vectors, and it's actually going to be equal to 10 minus 1, which is equal to 9. Right? And it's exactly this binomial coefficient that appears in there. Again, the details are not important. What is important is this generic theorem that tells you what happens when you apply a polynomial to a low-rank matrix is tight only when the matrix is arbitrary. It's completely arbitrary. And in here, this matrix is low rank, but it's very special. And that allows this rank to decrease by a quadratic, actually more than a quadratic factor in there, and you actually can gain a lot. There's a number of nice interpretations of what this number is. Let me not perhaps talk about this too much, other than perhaps the very first one, which is because this will appear when you explicitly write what the features are. So what's happening in there is that that number is really not just an arbitrary number. It's really the dimension of that feature space, where we look at the homogeneous polynomials in d variables of degree 0 to n. And in here, we look exactly at the same thing, replacing n with n minus 1, and we multiply each one of these terms by some power of s, where s is the sum of the squares of the variables. Right? OK, so what is a summary? The thing that I really wanted to understand were these two things come into place. The first is forget about the exponential, replace the exponential with a polynomial. And then when you apply this polynomial to this low-rank matrix, so this very particular Euclidean distance matrix, norm of x minus y squared, that's a low-rank matrix with structure. And this allows the rank to decrease. And in particular, we have a very good understanding of what the span, what the range of these matrices are going to be. Right? Now, this is great. This tells us something about the rank. Now, if you actually want to make this into an actual algorithm, you not only need to know the span of this matrix, the range, if you want, of this matrix, but you actually want the basis of it. And the problem, or the opportunity also, is that there's many, many bases that you can pick, right? Think about the case of, for instance, even if you think in the univariate case, if you think about polynomials of degree n, right? I look at the span of the set of polynomials of degree n, which is a span of the monomials, or I can think of it as a span of the Chebyshev polynomials or some other family of polynomials, right? These are both different bases of the same space. And if you're going to do any kind of numerical work, there's a real difference between a basis that looks like this and a basis that looks like this, right? One where all your vectors are nearly aligned versus one where all your vectors are orthogonal, right? It makes a big difference. Perturbations are actually going to behave in a very different way in one on the other. Again, well-known thing from numerical analysis, that if you pick monomials, monomials are just horrible. Well-known thing. Everybody should hate monomials. It's really like a dumbest way of doing anything. Why? Because exactly of this property that when n is large, there's really no difference between x to the 1,000 and x to the 1,001. They look like 0 and then blip. That's what all these vectors, they're going to start looking the same. They're still linearly independent, but they really look the same. And any error essentially will change one into the other. What's a good setting, for instance? There's many, depending on the setup, there's many alternatives. Classical solution, for instance, is to use Chebyshev polynomials instead, because they look like this. And you will not confuse one with the other by putting small perturbations. Right? If you take one of them and you perturb it in L infinity, if you actually put machine error on top of any of those, you're not going to confuse this polynomial with any of the other ones. These are really, really orthogonal in the model where you have nice perturbations. This is a one-dimensional picture. The higher dimensional picture is also well understood, but it's more notationally complicated. I will not tell you too much. There's something called harmonic polynomials. what are harmonic polynomials? It's really they're essentially polynomials where the Laplacian vanish. This is really the high order generalization of sines and cosines. When you think about sines and cosines in one dimension, these are really polynomials restricted to the unit circle. So now think about polynomials restricted to the sphere, right, to this n-dimensional sphere. And you want to essentially think about frequencies in the n-dimensional sphere. This is super well understood, something called harmonic polynomials. There's nice bases for them. And essentially what this space of features is that some kind of product space combination of functions that depend on the radial direction and functions that depend on the angular direction. Very much like in the Jacobi-Unger expansion that I talked about before. So this is really the expansion that you want to do. You want to expand your kernel using the formulation that I talked about before. In terms of this, in the radial component, you want to use some kind of orthogonal polynomials for the distribution of the radial direction. On the angular component, you want to use this higher order generalization of sines and cosines, this harmonic polynomials, and the technical tools that will appear. Essentially some kind of expansion of your Chebyshev polynomials that you use in terms of something called the Gegenbauer polynomials. Again, sorry for introducing all this crazy stuff. But why do we do this? Because it's kind of well known. This is the equivalent of the addition formula for sines and cosines, that we can expand those in terms of these higher dimensional sines and cosines. This is like, I don't expect, of course, that I think one understands at this point.
Right? This is how you get the lower factorization.
So
how you have lower factorization.
Yes.
Yeah.
So essentially, what this will up to this point, this is really about the univariate function.
Yeah.
Right now, this part will tell you how to write each one of those terms as a product of features of x and y. Right, and this is exactly what I was saying about before. Right, when you look at what happens in here, these features they depend only on the direction. Right? These features depend only on how far you are. And everything that happens in here is a product of something of this type and something of this type. Now, just for comparison, I'll compare it, I guess, in a little more detail. Where do random features will appear? Random features replace this exact factorization of spherical harmonics with an approximate factorization that comes from taking random features. Right? So there's a nice way of actually combining this with random features if you keep the Chebyshev expansions type things, and when you use this for the angular part. But let me not expand on that. Right. Good. So let me just show you some empirical results. Yes.
So you still have n squared such things?
I have a sum of n terms. No, I don't have n squared.
No. Per x and per y, you need to compute this.
Yeah, but what do?
Factorization map.
You compute the feature map. Given an x, given my n points, for each point, I compute this feature map.
Okay.
That will depend only on how many terms I have in the expansion in here, and what's the dimension of the space of harmonic polynomials of n variables and degree b. Some binomial coefficient also that appears in that.
It's the next line, Sean. It's this line.
It's the next line?
Yeah.
I'm always missing one line.
It's that line. No, that's the line, right?
Yeah.
It's the y in case. The y in case.
So
will
this-
depend on the individual
Okay.
point, yeah.
So
You rewrite.
Yeah.
Yeah.
I missed it.
I mean, there's a lot of stuff to unpack in here. So let me just show you some empirical results. The point is, this is not only kind of fancy, kind of continuous math, but the point is all these things, they actually boil down to kind of orders of magnitude increase or decrease in either running times or whatever. Right. So as I said, there's a number of methods related to this, or things that people have used before to try to do the same thing. Tailored features we talked about before. They really use Taylor expansion, which I told you it's bad. Kind of they use some other things that are also horribly bad. Monomial bases, which is bad. Somehow they pull diagonal scalings, which somehow doesn't make any sense, because at some point you're computing exponentials of things like for narrow kernels, you're computing exponentials of really tiny things. So, Nystrom, that does something very interesting, which is because it uses data-dependent sampling. But on the other hand, kind of you do pay a price both for the randomness and for the somehow suboptimality of the kind of things that they're doing, because it's a spectral method and it's not something that actually takes into account kind of the entrywise type error. Random features, I talked a little bit about this before. Kind of versions of false multiple that kind of, again, they're great in low dimension, but because you pay this exponential price in dimension, because they rely on subdivisions of space, they very quickly kind of saturate in terms of how they work in terms of dimensions. So, okay, so this is a somewhat complicated plot, and actually it doesn't look that nice, I think, in here for some reason. Kind of just compares. So what's happening in here, so you're really, these are for different values, different dimensions, and different width of the kernel. Right, so in here, the kernel is very wide.
What's the data? Is it just random?
So in here, I'm just computing this is not about the data. This is how well these different methods approximate the kernel entrywise.
But the kernel itself is generated. You need the x and y.
Think about I produce all the points in the sphere, or all the points in the unit ball. Right, I'm really looking at the worst case error for if somehow the points are sufficiently dense.
Okay.
Right. So what happens in here? This is an easy case or easier case where the kernels are very wide. This is a difficult case where the kernels are very narrow. And as I said, in here we're increasing in dimension. And what we're comparing, the method in red is what we're proposing, this version of a Gauss transform. Blue is a Taylor one. Black is Nystrom, and kind of this other circle, I don't know which color it is, kind of is random features. Of course, these last two methods are randomized, so we're actually just computing the 10, I think, 10 samples and averaging. And what is being plotted in each one of them? This is a rank of the factorization that I use, and this is the error. This is the L infinity error that you get when you factorize. Right, and what you can see is that in pretty much all the regimes, kind of doing this kind of thing is actually kind of orders of magnitude better than the other things. Yeah, sorry.
So just a quick question about computation. So if I fix a particular rank, are the different methods in this plot going to take roughly the same amount of run?
Yes. Yeah. Somehow the only thing that determines how how fast is to operate this really is a rank. Because you're just multiplying by this.
If you form the whole matrix and do eigenvalue decomposition, what's the optimal answer?
I don't have it in here, but it will be worse. Because again, in here I'm measuring entrywise error. And eigenvalue factorizations don't necessarily give you good entrywise error. We'll see this actually in the, we should plot this. Actually, that's also so what's a large scale, I guess, feature of all this? Kind of our method does great. This is a regime where random features start doing well, where you don't care about getting too good approximations. Kind of notice that the error in here, it's not that random features, for instance, is a lot better than this. It's that they're all bad. Right? Kind of the error in here, kind of for these ones is 1, for this is kind of 0.8. Right? So the vertical scale of the things is actually different, from one point to the other. So, okay, good. So if we want to talk about specific task, specific classification task, this is a case, for instance, I think we're doing some least squares classifier, some SVM type thing. Kind of, so the first line in there is exactly what we talked about, actually using the full kernel, doing dense linear algebra on this 14,000 by 14,000 matrix. This is slow, takes like 20 seconds or something like this. And these are the numbers that you get in terms of training error and test error. The point is in here, we can do this kind of 30 times faster or something. And the errors are essentially the same. Nothing kind of changes. If you look at either Taylor, Nystrom, or RFF, I mean, you do perhaps faster, perhaps not that much faster, but the accuracy can actually go down.
Right. Wait, how is it faster? It's 10 seconds.
Sorry?
Like Taylor and Nystrom.
Well, 20 versus 10.
No, but compared to your method, why is your method so much faster? You need to say it's the same computation.
Rank is small.
No, because we use a smaller rank.
I see.
Right? Because we want to achieve a certain precision. Achieving a certain precision allows us to use a smaller rank. Smaller rank gives us better computation. Again, sorry, I need to finish. Kind of, what's the basic idea? Even though this is a super well-studied kind of problem, if you're bringing nice, very classical tools, kind of either from approximation theory or actually, I guess in that case, it's either pretty straightforward or use fancy algebra to get this ranks, you can actually do a lot better. Kind of, the basic principles are really forget about Taylor, forget about monomials, really use what state-of-the-art numerical analysis people do, kind of, and kind of you can do things a lot better. The paper should be up, kind of probably in a week or two. It's almost done at this point. And thank you for your attention.